I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
Space. Time.
the brain,
Life. The universe.
This week, we're delving into physics in a galaxy far, far away. And if that's not a big enough giveaway, we are, of course, probing the science of Star Wars.
Plus, in the news, evidence that London air is stunting the growth of developing babies, and scientists use AI to decode what dolphins are saying. I'm Katie Haylor.
I'm Chris Smith, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
First up this week, air pollution from road traffic in London is adversely affecting fetal growth and leading to low birth weights. That's the conclusion of a new study that's come out this week from scientists at Imperial College. And what's very worrying about it is that the affected mothers were exposed during their pregnancies to pollution levels that were only about half of what's currently set under EU law as the safe limit for human exposure. Leading the study was Mireille Toledano.
We took every single singleton live birth in London during 2006-2010, that's a 5-year period. And that means we actually were looking at 540,000 births. And we then estimated the residential exposure of every mother during her pregnancy to various different air pollutants, in particular small particulate air pollution, which is mainly a result of vehicle emissions. We then looked at the link between the air pollutants and the birth weight of every baby. And we then saw that for every 5 microgram per cubic metre increase in small particulate air pollution, there was a 15% increased risk in a mother having a low birth weight baby at term.
Those are big numbers, aren't they? So how did you actually, first of all, quantify the amount of pollution that each individual was being exposed to?
So across London, there are various different pollution monitors. Measurements from those monitors are then mapped, and then we are able to map down to a 20 metre by 20 metre grid for our air pollution exposures across the whole of London.
Are there not lots of other factors that could be playing a role here? For instance, if you live in a deprived area where there is more traffic, you're much more proximal to a road, you are therefore subject to much worse air. Could you not also be subject to much worse housing conditions in general, a poorer diet, a therefore higher risk profile for many of the problems that include low birth weight?
Yes, absolutely. It is very important to consider the other factors that do play an important role in a mother's risk for low birth weight baby. And socioeconomic status is one of those. We did take into account deprivation. What we did was adjust for that at the area level. So we assigned to every mother, based upon her residential address, what her socioeconomic status was for that area. So if it was a poor neighbourhood, we would assign poor neighbourhood. And if it was a richer neighbourhood, we would have an affluent score for that. It's not perfect, but it does a very good job at trying to take into account factors like socioeconomic status and the things that are correlated to it, like smoking. We did not have individual level information on, but we did our best to take into account that kind of information as much as possible.
What about noise as well? Because when one drives down a road, one makes a lot of noise. When you live near a road, you're subject to a lot of noise. We know that people who live near Heathrow Airport, on average, have higher blood pressure and a higher heart disease and stroke risk than people who don't live near Heathrow and other busy airports. So could not noise just account for this?
Yes, absolutely. That was a very important question, and that's something that hasn't been addressed in any previous research study on this kind of scale before. This was the largest study in the world to look at that question as to whether the effects that we are seeing on low birth weight, are they really from the air pollution, or could they be from the noise, or from both? We actually found in our study that although traffic-related noise could potentially have that impact, we did not see an independent effect of traffic-related noise on low birth weight throughout London.
So what should the Secretary of State for Transport take away from your study? Not that they're going to read it, but having listened to this programme, what message should they take away?
So I think the key message for policymakers is that the current legal limits set by the EU for small particulate air pollution are 25 micrograms per cubic metre. The average pregnancy exposures to small particulate air pollution of the women in London is 14 micrograms per cubic metre. In other words, our current air pollution levels for small particulate air pollution are actually much lower than the legal limits, and therefore it's absolutely clear that we have seen adverse health effects at these lower limits, and therefore our current legal limits are not safe. They are not protecting our pregnant women, and they're not protecting their unborn babies, and they must be reduced.
Strong words. It's a worry, isn't it? Mireille Toledano there. She has just published that work in the British Medical Journal.
We live in an increasingly interconnected world. There are now smart fridges that order your shopping when certain foods run low, and even intelligent pills that will tell the doctor when you swallowed them. Now, the UK's Engineering and Physical Sciences Research Council have funded a £1.5 million project to get products, production lines and manufacturers talking to each other. And angel investor Peter Cowley has been taking a look at what they're planning. So, Peter, this phrase chatty factories is being bandied about. Can you tell us what is a chatty factory?
Hello, Katie. Yes, a chatty factory, I think, is a term that's been produced from this grant. As you say, it's a grant done by academics throughout the UK. Chatty factory in that the product will chat back to the factory. So let's just explain that. The ability for a product, once it left the factory, to chat back, it needs some sensors and it needs some connectivity. So the sensors could be strain gauges, they could be temperature, could be humidity, etc., could be location even. And that data is then passed back from the device, whatever it is, consumer device or industrial device, back to the factory. The factory will then use that information to make modifications to the process to improve the product as it moves out of the factory. Now, how long that feedback loop is, I'm not sure, but it effectively almost could happen instantaneously. So something happens out in the field and minor changes made to the process.
This is through the Internet of Things, right?
Correct. We've had our desktop computers connected for, 30 years, 40 years. We've had our mobile phones connected for 10 or 15 years. This is where it's not a mobile phone, it's a thing. And these things can be very small. They can be almost invisible.
OK, well, can you give us an example of what type of product might be hooked up to this feedback cycle?
Yeah, so the example given in the press release to do with this grant is a bike helmet. So you imagine a push bike helmet that has sensors on it. Those sensors could then detect something has happened, possibly it was dropped, possibly the temperature was too low or too high, and pass that back to the factory. So the factory could then change something. Now, it's unlikely they'll actually change the design, but they might change the process. So it might change the material, it might change the curing temperature, it might change whatever.
So is this changing something that is then going to be applicable to literally that product, that, say, my bicycle helmet, or is it for future designs of that same helmet that are going to be making their way into the stores? Good
question. No, it won't change the helmet you've got on your head, but what it will do is change the next ones that come out of the factory. Either that maybe even the same day or over the next few weeks or months. Can I just point out, though, that the bike helmet is not a very expensive product, tens of pounds, and the actual cost of manufacture is a quarter of that. So adding sensors to a bike helmet, I'm not sure makes that much sense.
That seems a relatively simple thing to do. This grant is quite large, £1.5 million. Why do they need that much money?
It's being spread between 5 research departments in 5 different universities, so they obviously have to be working together. It'll be used primarily not for the sensing, I suspect, but for the processing of the data. So the reason that it's so relevant and connecting products back into the factory, I had a car in the early 80s that would actually tell through the garage what was wrong with the car, not connected in real time, but would tell that. What's enabled this is Internet of Things, which are coming on rapidly, and also big data crunching, machine learning, deep learning.
What's the motivation for this? Is this we want to improve our products and ultimately make more money? Is there another motivation?
There will be a number of motivations because this process within factories has been going on for decades to some extent. More reliable products, so therefore the warranty claims will be less. The consumer will feel happier about it because things won't be breaking. Also, the factories will be able to produce less of something that's not selling very well, possibly because of usage. The bike helmet's a bad example there, but I found an example where, for instance, adjusting clutch pedals, there's some regions of the world don't ever adjust their pedals on a car. So if that could be fed back to the factory, they wouldn't offer that product in the future.
Oh, I see, because you know how much it's being used, and if it's not being used very much, you can just take it out.
Correct.
What about this data? Companies have this data, your usage data on products. Is there a question around the security of that data?
There is with any interconnected devices. So it's not just the companies having that, and you sort of trust that the company you buy from will look after it. It's the connectivity back to that factory. So it's what between the device, which might be a helmet or whatever, and going back to the factory. If that's intercepted, now there's actually part of the grant specifies that. They definitely will be addressing that security of data. The whole world is moving in that direction. We're all worried about our data leaking.
Peter Cowley, thank you very much.
Thank you, Katie.
Got a biological brainbuster or a chemical query? Ask the Naked Scientists.
I just wanted to know about sleep paralysis. Is it a disorder or condition, and can it be cured?
How much energy is in moonlight? And could solar panel technology be used to capture this energy?
When you cook food with any alcohol, how much, if any, percentage of the alcohol stays behind?
Every Friday, the Naked Scientist and Cape Talk unravel the science behind those weird and wonderful questions you've always wanted to ask. Download and listen for free at thenakedscientist.com/ask, or simply search and subscribe to Ask the Naked Scientist on your favourite podcast app.
On the way, we're finding out how researchers have learned to talk dolphin, and we're looking at the science of Star Wars. And those planets that you see in those films, have researchers discovered their real equivalent? Stay tuned. Before that, though, for the last 400 years or so, the convention has been that scientific research is published in official journals. These follow a strict code of conduct, they're recognised internationally, and they present trustworthy information that other scientists and the general public can rely on. But in recent years, a new breed of publication has appeared that lacks these guiding principles and morals, and they exist only to make money. The problem is that the costs are not just financial. These publications are vehicles for fake science. They're named confusingly like well-regarded official journals, and they're proliferating very rapidly. I spoke to Manoj Lalu from the University of Ottawa, and he's been studying the phenomenon that is these so-called predatory journals.
So a predatory journal is basically a journal that doesn't follow the usual processes of a regular journal. So a regular journal, when you send in a scientific piece, they will review it. Then if they deem that it's something that's worthwhile, they'll send it out for peer review to several scientists usually who are experts in the field. Those experts will give feedback. The paper is improved, the study is improved, and then if the paper is accepted to the journal, then it gets published. In a predatory journal, basically what happens is a paper gets sent in, and more often than not, there is absolutely no review process. They just publish it immediately for a fee.
And that's the motivation, is it, to make money?
Absolutely. So these are big money-making ventures. There's so many of these journals right now that we know that's obviously a profitable venture as well.
When you say there's so many of them, how many are we looking at?
So the current estimate right now is that there's about 400,000 articles in predatory journals.
And where are they all based, these journals? Are there certain countries that are pushing this, or are they all over the place?
So it's interesting. Many of these journals will say that their mailing addresses are in the US, UK, or in Canada in some cases. However, many of them are actually based out of India or other developing nations or newly industrialized nations. That being said, what's very interesting is that many of the articles being published from them are actually coming from upper middle income or higher income countries.
Now, is that because people in upper and higher income countries want to just publish something, or are they being deceived by this machine and they think they're receiving proper scientific treatment, but they're not?
Unfortunately, I can't directly answer that. I can only speculate what the motivations are for people who are submitting. I think there are some people being deceived. So that's really goes under the why these journals are called predatory. They're looking for prey, and their prey are unfortunate scientists who are unaware of where they're actually sending their particular work. I think there's another group of folks who maybe are trying to pad their CVs. The way people are advanced through academic circles is through the quantity of papers that you publish. If you have many papers published, that looks very good on a CV as you're applying for promotion.
Those people aside, why are the people that think they are sending their science to somewhere legitimate, why are they being and how are they being deceived?
Many of these predatory journals actually have names that are very similar to legitimate journals. So, for instance, the flagship journal of the American Heart Association is Circulation. There is a number of predatory journals with very similar titles. So for researchers who aren't very familiar with the field, they might actually be thinking they are actually submitting to Circulation when they are not.
But apart from taking a few dollars here and there off of people who are duped, why is this a problem? In what way could this do harm?
So there is some work that has definitely been legitimately done, we think, that's been published in these journals. But I also think there's another category of people who are publishing really what's fake science. And I can tell you a personal example of that. So my mother-in-law, who's unfortunately passed away, she passed away from breast cancer. When she was ultimately at the terminal stage of her disease, she was really desperately looking for other alternative treatments. So she went to an alternative medicine practitioner. They said, you should take this infusion of this particular vitamin, and they provided a paper. And the paper, when she gave this to me, was actually from a predatory journal. So this alternative medicine practitioner had basically written up a review and published it in this predatory journal, and was now using this to basically dupe patients, saying there's evidence that it works, when clearly this was something that really had no evidence to begin with. This sort of demonstrates the harm that these journals can actually do to patients and public directly.
Given that there does therefore seem to be a serious threat, and given the numbers of papers that you're talking about, very large numbers, clearly something surely should happen.
Oh, absolutely. So I think there's a few different fronts that we can look at this. Number one, as taxpayers, we can apply pressure to agencies that are funding some of these work to make sure that they have policies in place to prevent researchers from publishing in these outlets. And as well, when you're giving a donation to your health charity, you can also say, hey, what are your policies as you start to distribute this to researchers in terms of where the work is going to be published?
Manoj Laloo, and Manoj has got a comment piece in the definitely non-predatory journal Nature Human Behaviour this week. He's looking at the strategies that we can use to deal with the problems he's identified. He's also written an article about his investigations, which you can find on the Naked Scientist website. That's at nakedscientist.com/articles.
It sounds very worrying, doesn't it? Now it's time to come down to earth.
What happens when the science and technology of space comes down to Earth? Welcome to Down to Earth from the Naked Scientists, the mini-series that explores spin-offs from space technology that are being used on Earth. I'm Dr. Stuart Higgins. This episode, how what started off as NASA trying to tidy up its website ultimately helped in usher the era of cloud computing. We're all told to be careful what we post online, but when you're a large organisation such as NASA, keeping track of what's on your website is a challenging task. And in 2008, when NASA was trying to clean up its web presence, the agency realised they needed more than just a spring clean. Not only does NASA share images and results from space missions, it also uses a myriad of computer networks to store mission data. Engineers soon realised they needed a better way for people to access the data and computing power on their network. To do this, they developed the software needed to create their own cloud. While they may sound fluffy and nebulous, clouds are very much real things. They are, in essence, just a large number of computers that are connected together and can share different computing tasks. Racks of computers will often be found in a warehouse, more elegantly called a data centre, located somewhere with a fast internet connection. When you access a cloud-based website or service, your computer or smartphone is talking via the internet to the computers making up that particular cloud. Take, for example, watching streaming videos on the internet. Your smartphone is talking to a computer on that company's cloud. It will find the right video, most likely stored on another computer somewhere else on the same network, and send it back to you. The clever part is that the sharing of jobs between different computers means that if a company suddenly needs more space, due to, say, a surge in people sharing cat videos, they can simply plug in more computers, and these machines can quickly add their resources to the bigger cloud. And rather than just serving up cat videos, the cloud can also run applications just like your computer at home. You let the computers in the cloud do the heavy lifting and get them to send you the results back to your machine. For all that to work, you need software that can coordinate all the different actions of the computers making up the cloud. This is what NASA, together with a firm that runs cloud computer systems, developed. In 2010, a joint consortium launched OpenStack, an open-source cloud software platform. Open source means the computer code is free for anyone to use without the need for a license, and it was this feature in particular that prompted the widespread uptake of cloud computing. Before this, it was still a relatively new concept with only a few commercial players in the market. Today, companies such as car manufacturers, supermarkets, and financial services firms use the OpenStack platform to power their own clouds. So that's how what started off as trying to make it easier to share the results from space missions helped to promote the widespread adoption of cloud computing. That was Down to Earth from Naked Scientists. My name is Dr. Stuart Higgins, and you can find more episodes online at nakedscientist.com/downtoearth.
Thank you, Stuart. And next time on Down to Earth, Stuart finds out how a drill technology, originally destined for Mars to help scientists look for life, can now help to rapidly recharge your electric car in the garage.
Sounds interesting. Now, dolphins are exceptional in the variety of sounds that they can make, and as well as being able to communicate with each other through a complex language of whistles, they also use echolocation clicks to hunt down prey and to understand their immediate surroundings. Now, a team at the Scripps Institution of Oceanography in California have developed an artificially intelligent system that can spot patterns in these clicks and then assign them to the species that made them. Learning this lingo should hopefully improve our ability to monitor dolphin populations and also to understand more about their behaviour. Lewis Thompson heard how it works from its creator, Caitlin Frazier.
Dolphins make 2 to 3 main categories of sound. They make whistles, which are communication-oriented, and then they make these echolocation clicks, which are like bat sounds. They're really high frequency, very short, like microseconds long, kind of laser beams of sound that they produce out of their forehead. They have an organ up there called the melon that focuses the sound like a lens, and then it comes out of their forehead and bounces off of things in the environment, and then the reflection comes back, and based on that reflection, what frequencies come back and how fast, they can interpret if there's a target in front of them, what is it, how far away is it, is it hard, is it squishy, is it something to eat, that kind of thing. So they're producing these signals constantly, and we as scientists are able to eavesdrop on those signals and use them as a tool for studying dolphins. So we build acoustic recording devices that will sit on the seafloor and record these sounds for very long periods of time.
And what's different about the way that you're trying to study these sounds?
As a grad student, I spent a lot of time looking at data manually, looking at echolocation clicks. Specifically, I work in the Gulf of Mexico, and so I had millions of these echolocation clicks that I had detected in data, and I spent a lot of time staring at computer screens thinking, okay, I think this type is different from that one, trying to wrap my head around what the similarities of some were versus others. And then I realized, I think it would be better to use a computer to do this consistently. And so what we're doing now is trying to use unsupervised learning. So it's this idea of, I don't know exactly what's in this data set, but I'm going to use computing techniques to tell me more about my data without me telling it upfront what it needs to find. So trying to use those to see if that can help us understand our acoustic data better.
So instead of telling the computer that this click is produced by this species of dolphin, you're letting it work it out for itself. Is that right?
Right. So we're using these network analysis tools to aggregate lots of similar dolphin clicks together. And what we're looking at in the dolphin clicks is frequency content. So frequencies are, there's low, there's really high pieces, and those vary between species. We think some species, it may have to do with how their head is shaped. So we're using that, and we're also using the rate that they're clicking at. So some click slower on average, and so we're using those two pieces of information combined to look for unique click types in our data set.
And how do you know if it's doing this correctly? Is there a way of checking if it's right?
So for now, what we're doing is comparing it to what a human analyst would do, but on a smaller data set. So we have a data set that a human has looked at, and then we run that using the computer and we compare. So for example, Rizzo's dolphin have a very distinct click type, and that has sort of emerged from the unsupervised process, which gives you a sense that it is doing something. But the next step is really going out into the field to just see if we can figure out what species or genus is making these different click types.
How do you think this computer approach will help change our understanding of dolphins?
So these clicks are produced by all of the animals in a population, and they're in large numbers. So by recording these clicks, you can do a lot of back calculations to estimate how many animals are swimming through the area over time and look at how populations are changing. And so what this research is doing is trying to take it to the next level, not just how many are there, but who, like what animal, what species, what genus, those sorts of questions, so that we can start to get a more detailed picture.
It would be interesting to find out what they're saying, wouldn't it? That was Caitlin Frazier there telling Lewis Thompson about the study she's just published in PLOS Computational Biology.
And a lot of people ask us on The Naked Scientist how you can find out more about the programme content and whether or not we transcribe the programme. We do. If you go to nakedscientist.com/podcasts, the programmes are all archived there. There are transcripts of each programme broken up into each of the individual components alongside the references to the original published papers that the reports are based on. In the next half an hour, we're going to be exploring the science of Star Wars.
We're on a mission to spread science throughout the galaxy. We'll be pondering planets, investigating intergalactic travel, and studying space-age technology along the way.
Indeed. Shortly, Katie is going to be talking about the rockets and the spacecraft of the future. But first, we're going to look at where those rockets might actually take us. And one likely destination is another planet, probably one outside our own solar system. These sorts of planets are called exoplanets. They're planets that orbit a star other than the Sun. So far, more than about 4,500 of them have now been discovered. And space scientist Paul Rimmer is here to tell us about some of these planets. So, Paul, first of all, how do space scientists like you find these planets? How do they do it?
One of the ways in which they find these planets is just by looking for them. So they can see these planets either from the light that's reflected from the star off the planet or from the light of the planet itself. It's very important, if you're going to do that, to block out the light of the star because the star is so much brighter than the planet itself. Another way is very much like if you've looked at the transit of Venus. It's the same sort of idea. You have a planet passing in front of our sun. You can also have planets passing in front of other stars. Now, these stars are so far away that you're not really going to be able to see the planet passing in front of the star, but what you can see is you can see a little dip in the light of the star.
You see the effect of the planet on the light rather than see the planet itself.
Exactly. And depending on how prominent that effect is, you get an idea about the size of the planet.
How? What? Because it makes a big hole in the light coming to you, so the light dips or something?
Yeah, so some of that light is blocked, and so the light goes down a little bit, and the amount that the light goes down depends on that cross-sectional area of that planet.
And presumably how often it does that tells you how fast it's going around the star, and that tells you therefore how far away from the star it is.
Absolutely. Absolutely.
What else can you do? Because presumably the planet is exerting a gravitational effect on the star. So can you exploit that as well?
Absolutely, yeah. So you can actually look at the star, and the star will have a certain color. As the planet goes around, the planet pulls on the star and causes the star to wobble away from us and towards us a little bit. And that makes the light a little bit bluer and a little bit redder. And from that, how fast that happens, you also get an idea of how far the planet is away from the star. And by how much that happens, you get an idea about the mass of the planet.
So you can physically weigh a planet you can't see around a star that's light years away.
Yeah.
If you know the mass of the star, does that then tell you roughly what it's made of? Because you can get some idea as to where it's orbiting and how fast and how much it's making the star wobble. So can you infer the mass of the planet from that?
Yeah. With all of these methods, though, it's very important to understand the star very, very well. With the transit method also, you only know the size of the planet as a ratio of the size of the star, so you really need to know the size of that star.
Can we work out what these planets are made of, though?
Yeah, so as we were just talking about, from this transit method, you get an idea about the size of the planet. And from this radial velocity method, this is looking at the wobble of the star, you get an idea about the mass of the planet. So if the planet has a density of around 5 grams per centimeter cubed, then you know that it's probably rocky, like the Earth. And if it's something more like 2 grams per centimeter cubed, then it probably has a great deal of water. And if its density is much less than that, then it probably has a very gaseous envelope of, say, hydrogen and helium.
And what about the conditions that one might experience if you were transported to this world?
One of the things that you could look into is whether the planet actually has an atmosphere, and you can tell that through the transit method. You can look at the planet passing in front of its star at different wavelengths of light, and maybe the planet looks smaller in red light and larger in blue light, and that tells you that the red light passes through something more easily than the blue light passes through, and that's generally an atmosphere.
Now, how far away are these planets that you and your colleagues are looking at and exploring? I mean, are they in our cosmic neighbourhood, or are they a considerable distance away?
Quite a few of them are in fact, in our sort of cosmic neighbourhood. It's still vast distances, by the way, that I tend to travel. Some of them range from just a few light years all the way to thousands of light years away.
Now, if you can tell all this about the atmospheric composition and the likely temperature and what the planet's made of itself, does that mean you can also ask hard questions about the possible existence of life processes? Because we know there are some molecular signatures that go along with life on Earth. If you were looking at the Earth from space and you asked those questions of the light coming from the Earth, you could tell there's probably life here. So can we do that for these exoplanets?
Potentially so. It's a challenging problem. And again, it's a problem where you really need to be able to understand the star itself. So if it was an Earth-like planet around a sun-like star, you could in fact look for these particular signatures in the transit. You could maybe see oxygen and methane and nitrous oxide. And if you saw all 3 of those, that would be a very good indication that there was life. One of the problems, though, is that a lot of these planets are found among much smaller, cooler stars. And these smaller, cooler stars are much more active in the ultraviolet. And that can actually end up producing some of these things like oxygen in great abundances without life being there at all. So you really need to be careful.
Anything that we've spotted so far that bears any remote resemblance to those sorts of worlds that they go visiting in Star Wars?
One of the planets, which comes out of my favorite exoplanetary systems right now, is TRAPPIST-1F, which is, as far as we understand, a pretty cool planet. We don't know if any of these planets have an atmosphere, but if it does have an atmosphere, and if the atmosphere was very much like what the Earth was in its infancy, then it would be very, very cold there. And in fact, it would be almost entirely covered with ice, except for this one side, which is always facing its star, which would be like a giant blue ocean. And it might be likened to the sort of ice planet Hoth, at least on one of its sides.
Would it be a nice place to go or not?
If you were a bacterium, it may not be so bad in the ocean. Otherwise, I probably wouldn't recommend it as your first travel destination.
In that case, I'll keep my feet firmly here, down on the Earth. Thank you very much. Paul Rimmer from the University of Cambridge.
So it sounds like there are some pretty exciting planets out there, but will we ever be able to explore them? In the Star Wars films, practically everyone is accustomed to hopping from planet to planet, whether it be in an Imperial Star Destroyer, an X-Wing fighter, or the Millennium Falcon itself. And here to talk to us about space travel is Liz Seward from Airbus Space and Defence. Liz, welcome. So can we start with a traditional rocket? First of all, how does it work?
Well, rockets have been around for a really long time. The first known rocket is actually from 400 BC in Greece, where a steam-powered pigeon flew down a wire. So it got propelled by steam out of the wings.
Wow.
Then the Chinese filled bamboo tubes with gunpowder. They actually used them to fire arrows in war, and then they turned them into fireworks. And so it's been around for a long time, but modern rockets really came about from the early 1900s when they started looking at liquid propulsion and making them bigger. And so our rockets nowadays work either by using solid rocket boosters, like giant versions of the Chinese rockets. They were the boosters on the side of the space shuttle. And it's a mixture of fuel and oxidizer mixed together as a solid. And once you set fire to it, it will continue to burn until all that fuel is used up. So there's no way of turning it off. So then we have liquid engines where you have big tanks, one with an oxidizer, one with a fuel, and they meet in a combustion chamber. And then as they ignite, fire and gas propels itself out of the end of the rocket. And this is better because you can turn it on and off by controlling the gas flow. And if we go back to our physics from school, Newton's third law says if you've got a force in one direction, you have to have an equal and opposite force in the other direction. So you shoot this hot, burning gas at high speeds out of the end of your rocket, and that propels you up, and in our case, out of the atmosphere and into space.
So what are we using rockets for now? Are we using them for space travel?
Yes, we use them to get out of the Earth's gravity well. We sit inside the gravity well of the Earth. And so we fire ourselves up into space, into orbit. And at the minute we take people to the International Space Station or satellites to orbit the Earth, from telecom satellites to your GPS signals to things exploring our solar system.
So on that note then, as we're getting to the end of the year, what are the biggest achievements that have been made in space travel?
Well, we're looking at ion drives at the minute. They're used in Star Wars to propel themselves around the solar system. And it's ions as in atoms and molecules that get fired out of the back of a spaceship. In our case, we're using them in satellites. In Airbus, we are changing our chemical propulsion systems once in space to ion drives, electric drives. And they work by firing tiny charged particles out of an engine. So the thrust that you get is very low, but you can do it for a very long time. So we changed the travel journey from near-Earth orbit to geostationary orbit, 36,000 kilometres away, where all of the telecom satellites sit. It takes 3 days with chemicals and 6 months with an electric propulsion, but you save 40% of your fuel mass, so you can take 40% more payload or have a smaller, cheaper satellite. So it's very attractive.
Is this an example then of taking something from sci-fi through to sci-fact, something that was originally in Star Wars and then we started working on it, or the other way around?
Oh, that's a good question. I think that science fiction has been looking at this for a long time, but earthbound versions of the way this works have been studied in physics for a really long time too. So I think it's earthbound physics inspires science fiction writers, inspires earthbound physicists again to make it real.
That's an excellent cycle. So looking ahead then, what do you think will be the next big leaps?
Nuclear engines. One way is to have a small nuclear reactor that heats up your fuel really, really hot, which means it can go much faster. And if we do this, it can be 2 times as efficient as our current rockets. But in the 1970s, there was a project by the British Interplanetary Society called Project Daedalus, which looked at using fusion, deuterium and helium-3 to power a rocket that could take you to Barnard's star in 50 years. The star is nearly 6 light years away, and you'd have to build it in orbit. And we're getting closer to that, but one of the limitations is helium-3. It doesn't occur very naturally on Earth. We'd have to mine it from the moon, or in the proposal, they actually would send a hot air balloon to Jupiter to mine it in Jupiter and send it back to Earth.
Okay, so how on earth do we end up getting helium-3 then? Is this a possibility?
We're getting closer to be able to mine it from the moon. We definitely know we're near getting it from Jupiter in a hot air balloon. But one big push at the minute is having a moon village. It's proposed by the European Space Agency, and the rockets being developed. The Americans have something called the SLS rocket. It's just a bigger version of our current ones, but their plan is to go to the moon and then Mars. And people are really interested in going to the moon because you can mine helium-3 there. And if we get that in large quantities, it may change the way that we produce energy, and it may also change how we do space travel.
Thank you very much, Liz Seward.
Still to come, what Star Wars technologies in the future might become a reality. We'll find out. Before that, though, travelling through hyperspace to explore distant planets sounds all very good, but all of that light-speed travel could have a slightly unpredictable and unusual effect on how we would experience time. Heather Walk has been researching relativity.
Space is a very big place, and to get anywhere at a reasonable rate, we're either going to have to cheat and bend space to create shortcuts across it, or more realistically, travel extremely quickly at or close to the speed of light, which is the fastest that theory says we can go. But flitting around the universe at these sorts of speeds could have some unfortunate side effects, not least for the aging process. For a start, Star Wars twins Luke and Leia Skywalker would actually finish up being years different in age by the end of the story. Why? Because of Einstein's theory of special relativity.
One of the basic assumptions of special relativity is that the speed of light is the same no matter how fast you're moving.
Cambridge University physicist Harry Cliff.
And when you go at very, very high speeds, close to the speed of light, strange things start to happen. The laws of physics are very different to the ones we're used to in our everyday lives. So, for example, time runs at different speeds depending on how quickly you're moving. Distances can stretch or contract, and everything is just rather unusual and peculiar.
Indeed, it is, because if I were travelling in a car at the speed of light and turned on my headlights, I would measure the light travelling away from my car, illuminating the road ahead, as travelling at the speed of light. But a policeman with a speed camera beside the road would also measure the lights from my car as approaching him only at the speed of light, not twice the speed of light. This seems totally wrong, because if I get my friend Lewis to stand a few yards away and shoot me with his dart gun, it hurts a lot less than if he rides towards me on his bike and shoots me again. Because this time the dart is travelling faster, having been launched from a moving bicycle. And we can prove this is happening if we do a slightly more accurate experiment with the help of physics teacher David Tricker from the Perse School in Cambridge.
So we've got a trolley here with a projectile launcher on top of it, so we can launch a ball vertically upwards from the trolley. When the trolley's stationary, not very surprisingly, the ball being launched vertically upwards comes straight down again and lands in the trolley.
Now, if we do the experiment again and make the trolley move along and fire the ball upwards, the ball still lands in the trolley, because the ball has the trolley's motion and its own motion relative to the trolley.
When the trolley is moving, the ball is launched vertically upwards from the perspective of the trolley, but of course we watching the trolley move see that the ball is also moving horizontally. So that means when the ball goes up, it then comes down again and meets up again with the trolley, so it lands on the trolley.
Yay! But with light, this doesn't happen. It always travels at the same speed of light for any observer. And the mind-boggling implication of this is that when you move at the speed of light, time has to change to keep the speed of light constant for everybody. Einstein realised this would happen himself, and he came up with a thought experiment called the twin paradox to explore it. Harry Cliff again.
So the twin paradox basically is looking at this idea that time runs at different speeds depending on how fast you're moving. So let's say you have two identical twins, they're exactly the same age, and one of them stays on Earth and the other one goes on some really long journey into space at close to the speed of light. Then because time runs at different speeds depending on how fast you're moving, the twin that's travelled out around the universe and comes back, well actually, for him or her, less time will have passed than for the one left on Earth. So let's say it's Luke Skywalker leaving Hoth in The Empire Strikes Back and travelling to see Yoda on Dagobah. So if, say, he's got a wristwatch, he, say, leaves Hoth just after the battle and he goes at, very close to the speed of light, arrives at Dagobah, he'll measure a certain time. It could be like, a couple of days or something. But if Princess Leia, who's still on Hoth, is measuring how long that took, she might measure a much longer period of time. So she might measure several weeks or even months or years, depending on how close to the speed of light Luke's been travelling.
And in fact, in one of the journeys documented in The Empire Strikes Back, Leia would end up more than 2 years older than Luke when they finally reunited. But this isn't fanciful theory. We know it happens, and we've got good experimental evidence that Einstein was right. Time does change when we travel very fast, and we use this fact every time we turn on a GPS device.
These GPS satellites orbit the Earth, they're moving quite quickly, so time runs at a different speed for them than it does on the Earth. And the way that GPS works is by having really accurate clocks that communicate with each other to exchange time information. So you have to be able to take into account these effects. If you didn't, then GPS would basically wander away from, rather than having accuracy of a couple of meters, it would go to having accuracy of a mile or, several hundred miles over the course of quite a short period of time, and it'd be totally useless. So you have to take relativity into account if you want GPS to work, for example.
So it's all down to relativity, and perhaps that's why the actors in Star Wars all look so leathery these days.
That's Naked Scientist Heather Walk there, speaking with Harry Cliff and David Tricker.
So we've looked for Star Wars-like planets that we can live on. We've figured out how we can get there. We've even calculated how much we'll age and how much our relatives are going to age while we're doing that. Well, now it's time to ask a physicist about what technology perhaps we can reasonably expect to see in the future. Ben Allanach is that man. He's a Cambridge University theoretical physicist. First off, Ben, can we ask you about the Force? Because this pervades all of the Star Wars story, doesn't it, the Force? And is there a parallel for that in the real universe?
Well, every Star Wars fan knows about the dark side of the Force. And indeed, there are dark forces out there in the universe. There is definitely dark matter, which makes galaxies rotate at a weird speed. So if you try and work out how fast the galaxy should rotate from laws of gravity, you get the wrong answer, basically, than compared to observing how fast they go around the outside.
Zwicky spotted this.
That's right.
A number of years ago, made the first observations of these galaxies spinning. The stars are spinning at the wrong speed compared with how much mass we knew was there.
That's right. So if you add a lot of extra mass that you can't see, that's the dark matter, then that makes it rotate faster on the outsides and agree with observations.
So we think that there is this bizarre force, which we're calling dark matter because we don't know what it is. It's in a big halo or at least some kind of distribution around the outsides of galaxies, and it's gravitationally influencing stuff in the galaxy. But beyond that, we don't know what it is.
Exactly. We know it's a particle because if it's something that's big, you should be able to see it gravitationally lens light in the sky. So you look for these massive compact halo objects, they're called, and you look for a lensing effect that moves across the sky, and that you don't see that enough to be a big thing.
So it has to be some small particle, and it won't interact with anything. It won't talk to us in light because it's dark. So how do we find it then? How do we try and interrogate it?
So it might not have interactions with light, but it might have interactions with the weak force, which is responsible for radioactive decay. And in that case, you could conceivably produce it at the Large Hadron Collider in the collisions there between protons.
How would you know you'd made it, though?
The protons have equal and opposite momentum, and then you look for a final state after the collision, which is unbalanced in one direction. And you know that from school physics that, momentum's conserved. And so if it's unbalanced, there's been something invisible going in the opposite direction. And the invisible stuff is precisely dark matter, which takes the momentum off and sneaks it off like a thief in the night through the detector.
Now, we know that we've got a dark side. There's the good side as well, isn't there? So is there a counterbalancing force?
Well, unfortunately, not that we know of, but there is another nefarious force, which is dark energy. That's something which is even more mysterious than dark matter. It's making space accelerate across the universe, weirdly. When we look at other supernovae a long way away from us, they're accelerating more than they should do. We know that, everything's getting further apart. Space itself is growing because of the Big Bang. But there's an extra effect on top of that, this extra acceleration, and it's consistent with a small negative energy density of space itself. And it's making everything, accelerate even further away.
But what's bizarre about what you're saying is that space is making more space, accelerated by this notional thing, dark energy. And when it makes more space, the space it makes has more dark energy to make more space and make more space expand more quickly. So it's like it's getting energy from nowhere then.
The energy is kind of hidden in there from the word go. Space itself, this is saying, has an energy. It's a negative energy, right? So, in fact, you've got to be careful about whether you're taking energy away or giving it to the system. So, you're taking energy away by producing more space, but then that's pumped into the acceleration of planets and, whatever, various galaxies on the edges of the universe.
You gave us a suggestion as to how we might be able to find dark matter. How are scientists trying to interrogate dark energy to discover its nature?
We look at the afterglow of the Big Bang. It's called the cosmic microwave background. It's all around us in the sky. And small variations in its temperature tell you about what was happening in the very early universe, because that light's travelled since, just 100,000 years after the Big Bang. So since a long time ago. That light encodes some of the secrets of the universe. There's a technical thing. You can look at very particular bits of the light that have gone through a gravitational potential and then come out. You can do very precise measurements to see whether actually this acceleration was just to check whether it was happening. But actually getting to the nub of really what's causing it, I don't think we're very close to that yet. The work's all theoretical, and there aren't very many observational ways of telling the different theories apart.
As one theoretical physicist said, you have to be very cautious of maths and theoretical physics because you can prove anything you like on paper. Actually, it's whether or not it's really manifest up there in the sky that's a different matter. Wouldn't you agree, Katie?
I certainly would, yeah. We've got a few quick-fire questions for you.
In episode 4, Luke Skywalker blows up the evil Death Star by shooting proton torpedoes from his X-Wing fighter. Are proton torpedoes a real thing?
Yeah, proton torpedoes are absolutely a real thing, and they exist in the Large Hadron Collider. You have lots of these bunches of about 1 billion protons. That there are 8,000 in each beam, in counter-rotating beams. And okay, I don't know what you call the torpedo, but there's a length of them, a few meters long, and they're sent round at very close to the speed of light. You can't put your hand in the beam because it'd burn a hole through it.
So would it be possible to use as a weapon?
Absolutely, yeah. I mean, you could do. If you fired this thing out in space, the protons would travel a long distance. The thing is, if you use it in the atmosphere, protons are going to, lose energy pretty quickly, but it would still have a range. And if you could get enough power into the beam, it would be pretty formidable.
People are using this clinically, though, aren't they, to do cancer therapy, because you can fire a beam of protons into a tumour and they can be predicted in terms of how fast they'll slow down. And if they slow down and stop and dump all of their energy just in the cancer, they do a lot more harm to the cancer than the tissue around them.
That's right, yes. It's got advantages over conventional radiotherapy, where you get extra damage on the entry and exit of the body. It's not indicated for all cancers, but for, I think, particularly deep tumours, it's proved very useful.
So we've just got time for one more quick question for you.
Can I ever get my own droid, like R2-D2 or BB-8, to help me out with tasks around the house?
That's coming, I'm sure. We're getting self-driving cars. I think in the near future there's going to be self-loathing cars. AI is all over everywhere. That's science fact. That's not science fiction.
Ben, thank you very much. And thank you to our other guests this week, who are Paul Rimmer, Liz Seward, Harry Cliff and David Tricker.
And now it's time for Question of the Week. Heather's been having a blast with this question from Anthony.
Would a rocket launched from a tube, like a bullet from a rifle barrel, be assisted or hindered by that?
We fired off Anthony's question to Dr. Stuart Gray, researcher and lecturer in aerospace engineering at Strathclyde University.
Whether we want to send a spacecraft close to the Earth or much further afield, we need to start by going into an orbit. This is because using an orbit, or a series of orbits, is far more fuel efficient than blasting straight for our destination. This is because we are working with the gravity of Earth rather than against it. The particularly hard part about getting into an orbit is not getting to a high enough altitude, but getting to a high enough speed. For any given altitude, there is a specific speed that must be achieved in order for an object to avoid falling back to Earth. For low Earth orbit, this is about 7 kilometers per second or 16,000 miles per hour.
That's pretty fast. Most bullets only travel at 1 kilometer per second. That's not even close to 7. But what if we made a really powerful gun?
Firing an object from a tube or gun is a good way to get an object moving very quickly, as all the explosive energy is contained within the barrel and is used to accelerate the object along the barrel. For getting into orbit, though, even a very large gun would struggle to get an object up to the velocities required. even if your gun could fire an object fast enough. Another issue is that as soon as the object leaves the barrel of a gun, there's no longer any force from the propellant, and from there on out the object slows down. A rocket, on the other hand, is constantly accelerating as it carries all of its own fuel and burns it as it goes.
Ignition sequence start. 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
Right, so bullets start off fast and then slow down, whereas rockets start off slow and then speed up. Could we combine the two and fire a rocket out of a giant gun before turning on the engines so that it starts fast and keeps getting faster?
We struggle to reach very high speeds at sea level as we have to push through the air. Rockets spend the first portion of their flight gaining altitude to get above the very thick lower atmosphere before picking up speed where the atmosphere is much thinner. If our rocket was going too fast at low altitudes, the drag forces would be extreme and break the rocket apart. If we were to launch our rocket from the barrel of a gun, we could imagine that we would get some boost in initial velocity, but this wouldn't be any real help as the rocket would experience lots of extra drag as it exited the barrel. Overall, any small benefit in initial velocity for our rocket from launching from a tube would be outweighed by the engineering costs of ensuring it didn't rip itself apart due to the drag forces caused from travelling very fast at low altitudes.
Not sure our astronauts would thank us for that. Good to know. Thanks, Stuart. Next week, we'll be fishing for an answer to this marine musing from the Waite family.
Hello, Naked Scientists. We've just added a puppy to our family and we've noticed that he yawns a lot.
While we were watching Blue Planet 2 this week, that got us wondering.
Do fish yawn? Is there an aquatic equivalent?
If you think you know the answer, you can email chris@thenakedscientist.com, find us on Facebook, tweet @nakedscientists, or join in the debate on the forum. That's thenakedscientist.com/forum.
And that is it for this week. Thank you very much for listening, and thank you to Heather Walk, who put the programme together. Do join us at the same time next week when we'll be delving into the virtual realm of social media. The Naked Scientist comes to you from Cambridge University and it's supported by the STFC, the EPSRC and Rolls-Royce. I'm Chris Smith and thank you very much at home for listening. Until next time, goodbye.